what would a calculus class be without some optimization problems? You have done some optimization problems before in one variable, but now that we understand maximums and minimums in multiple variables, we're going to apply that to multivariable optimization problems. So let's start with a problem that says, find the minimum cost of an open rectangular box with a volume of 24 feet cubed. If the material costs are $1 per square foot for the front and back, $2 per square foot for the bottom, there is no top to this box, and then $3 per square foot for the other sides. Okay, so I've drawn the box for us, and then we'll have those dimensions be x, y, and z as I've shown in the figure. So the volume of this box is going to be x times y times z, and that's going to be 24. So what is the cost of the box? Well, the cost of the box as a function of x, y, and z is going to be $1 per square foot for the front and back. So the area of the front is going to be y times z. The area of the back is going to be y times z. So there's two of those at $1 per square foot. Then $2 per square foot for the bottom. So $2 times the area of the bottom, which is x times y. And then finally, $3 per square foot for the other side. So $3 times the areas of the other sides, which are xz. But there are two of those sides, so I'm going to multiply that by 2. And so now I need to minimize this function of 3 variables. But I have a constraint. That constraint is that x times y times z is 24. So I want to use that fact. I want to use the fact that z is equal to 24 over x times y. And I'm going to substitute that into my equation. So here, I really want to look at my cost of my box as being a function of just x and y. And so I'm going to substitute for z in this equation so that I can make it a function of just x and y. Okay, to see how to do that easily, I'm going to actually recognize that y times z is 24 over x. So that tells me that the first term is really 48 over x. The next term is just 2xy. And then the last term has an xz in it. So I'm going to divide by y and multiply by x. See, xz is 24 over y. Okay, so I get 6 times xz, which is 24 over y. 6 times 24 is 144 over y. Okay, so that's kind of a nice way to substitute in there. So c is now a function of just x and y. So I want to find the partial derivatives of c with respect to x and y. So let's see, let's do dc dx. dc dx is going to be, well, it's going to be negative 48 over x squared plus 2y. And I'm going to set that equal to 0. Then I have dc dy, taking the derivative with respect to y. First term 0, I'm going to get 2x minus 144 over y squared. And set that equal to 0. Okay, so let's see. Let's say that 2 times y, then, and using the first equation, is equal to 48 over x squared. So y is equal to 24 over x squared. And then what I'm going to do is I'm going to substitute that in to the other equation. Okay, so this is going to be 2x minus 144 divided by 24 over x squared. I'm going to set that equal to 0. Okay, so let's see. I'm going to get 2x minus, okay, 144 divided by 24 squared. So 144 divided by 24 is going to be 6. 6 divided by 24, because I'm dividing by 24 twice, that's going to give me 1/4. So this becomes x to the 4th over 4. I'm going to set that equal to 0. Okay, let's just do a little bit of easier manipulation, maybe multiply everything by 4. So I'm going to get 8x minus x to the 4th is equal to 0. So I'm going to get x times 8 minus x cubed is equal to 0. So either x is 0 or x is 2. Okay, but if x is 0, then I don't have a three-dimensional box. I just have I just have no dimension for x. So x can't be 0. That's not realistic, okay? So x must be 2, okay? Once I have that x is 2, then the rest of this is pretty easy to see. So here, I'm going to substitute that back in for y. So y is going to be 24 over 2 squared. So y is going to be 6. And then finally, I can get that z is going to be 24 over x times y. So over 2 times 6. So 24 over 12 is just going to be 2. And so those are the dimensions of my box. Okay. So here I'm going to get that x is 2, y is 6, and z is 2. Okay, so those are the dimensions of the box. Each one of those are in feet. Okay, so here I can put in feet. Okay, but how do I know that that's the minimum cost? Okay, so how do I know that I've found a minimum? Well, let's look at the second derivative test in this case. Okay, so let's find the Hessian for c. The Hessian for c in this case. Second derivative with respect to x is actually going to be 96 over x cubed. And then the derivative of with respect to x and then y is going to be 2. The derivative with respect to y, then x is going to be 2. And then I'm finally left with the derivative with respect to y twice is going to be 288 over y cubed. Okay, so that's my Hessian matrix. Okay, then if I plug in 2 and 6, what is my Hessian matrix? In fact, 96 divided by 2 cubed, so divided by 8, that's going to give me 12. And I have 2, 2, and then 288 over 6 cubed turns out to be 4/3. Okay, so the determinant of the Hessian of my cost function is going to be 12 times 4/3, which is going to be 16 minus 2 times 2, which is 4. So that's going to give me 12. So it is positive. And then the second derivative of c with respect to x is 12, which is again positive. So that tells me I have a minimum. Okay, so what is that minimum cost? Okay, that minimum cost is c of 2, 6, 2. And if you plug that into my original function, okay, that function, if you kind of go back up to the top here, which was 2yz plus 2xy plus 6xz, I'm going to plug that in, okay, and I'm going to get $72. Okay, so the cost of this box is in fact going to be $72 when I plug in 2, 6, and 2. Okay, let's move on to our second example. Okay, our second example of an optimization problem says a company sells both coffee and tea. If the price of tea rises, then the demand for coffee rises, and vice versa. The quantities demanded, okay, Q sub C and Q sub T, are given as functions of prices of C and T. Okay, so I have the quantity demanded of coffee is 500 minus 4C plus T, and the quantity demanded of T is 700 plus C minus 4T. Okay, well, what is the revenue as a function of C and T? So here I want to find a revenue as a function of C and T. Well, revenue is always going to be price. In this case, C is the price of coffee times the quantity of coffee sold, and then T, the price of tea times the quantity of tea sold. Okay, so this is going to be C times 500 minus 4C plus T plus T times 700 plus C minus 4T. So what is the revenue as a function of the price of coffee, C, and the price of tea, T? Okay, that's going to be 500C minus 4C squared, okay, plus CT. I'm going to save that one for later, plus 700T plus CT, okay, minus 4T squared. And I had 2 CTs, so there was a 2CT there. Okay, so there's my revenue function as a function of C and T. And then I just want to maximize revenue, okay? How do I maximize revenue? Well, I'm going to find the partial derivatives. The partial derivative of revenue with respect to C, okay, that's going to be 500 minus 8C plus, and this becomes 2T. And then I'm going to take the derivative of revenue with respect to T. Okay. Oh, I have made a mistake. It's always good to go through. No, I have not made a mistake. Everything actually looks just fine. So we'll just keep going. Okay. The derivative of revenue with respect to T, that's going to be 700 minus, okay, then I'm going to have 8T, and then the derivative of the last term with respect to T is going to be 2C. Okay. So let's write these equations out when we set them equal to 0. Okay, so I'm going to have negative 2T plus 8C is going to equal 500. And then I'm going to have 8T minus 2C is going to equal 700. Okay, I want to solve these two equations with two unknowns, T and C. Okay, so what I'm going to do is I'm going to multiply the top equation by 4. Okay, and then I'm just going to add up these equations. That way I get minus 8T plus 8T gives me 0. Okay, then I'm going to get 32C minus 2C. That's going to give me 30C. And then I'm going to get 2,000 plus 700. It gives me 2,700. Okay, dividing by 30, the price of coffee is going to be 90. Okay, so I'm going to plug that in. Okay, so I'm going to get negative 2T plus 8 times C, which is 90. That's going to equal 500. So that tells me that negative 2t is going to equal 500 minus 720 or minus 220. So t is going to equal 110. Okay, so I found my critical point. My critical point is that the price of coffee is going to be 90. I haven't really said what the units are, but that's okay. And then the price of tea is going to be 110. That's going to be my critical point. But how do I know that that critical point is a maximum? Okay, again, I need to find the Hessian function, okay, the Hessian matrix of revenue. Okay, so I'm going to take the derivative of r with respect to c. That's going to give me negative 8. Sorry, the derivative of the second partial derivative of r with respect to c is negative 8. Okay, then if I take the derivative of r with respect to c, then t, I'm going to get 2. If I take the derivative of r with respect to t, then c, I'm going to get 2. And then the second derivative of r with respect to t is going to be a negative 8. Okay, so the determinant of that Hessian matrix is going to be 64 minus 4, also known as 60, which is positive. Okay, and then I see that the revenue second derivative with respect to c is negative 8, which is negative. Okay, and that tells me I have a local maximum. Okay, so this is why it's going to maximize revenue. So if I want to maximize revenue, I need to charge, let's see, 90 for coffee and 110 for tea.